Yeah, so I've been thinking about mathematics education now for around 30 years, and I'm participating in the Yale Teachers Institute has been a very important part of that process, and so I'm very happy to be able to propose a new seminar on a topic that so one of the things that I thought about a lot in thinking about math education is important things that we don't teach. And students are somehow just supposed to get these things. And very often they don't. And this is what leads to a lot. I think this is an important aspect of student failure in mathematics. And in particular, with fractions, I think that students have to really change their idea of what a number is in moving from whole numbers to fractions. I mean, numbers start out as counts, and it's very easy. You go 1, 2, 3, 4, you just see what's there, and you point to them, and you rattle off the numbers. Actually, counting is hard too, but it's relatively easy, and so for small numbers you can do it. But a fraction is a different kind of an animal. Clearly, a fraction is not accounted for by a count. So what is a fraction? Well, the fraction essentially is a ratio. I think that's the cleanest way to say it. It's not usually introduced that way. They're introduced as like parts of a whole. But yeah, the whole is the essential thing. There's some unit, and then you have some other quantity of the same type. And then the fraction is telling you how big this other quantity is in relationship to the unit. And so it becomes very important to always keep in mind what the unit is. So one thing you have to do to teach fractions successfully is develop what I call unit consciousness. Always have your students keep in mind what is the unit they're referring to when they deal with fractions. But then it's important to understand how a fraction expresses a ratio. And so a fraction is written a over b, and the a and the b have very different functions in that expression. And the b is essentially telling you about dividing, right? What you do is you take the unit and you chop it up into b equal pieces, and then 1 over b is one of those pieces. And then the a tells you how many of those pieces you choose. Many students fail to see the relationship between fraction and size. And this is what really one of the biggest failings of learning fractions. Some people think that a fraction with a bigger denominator is bigger. There's a really nice story about this. Some years ago, McDonald's introduced it. It had these little teeny tiny hamburgers, and at some point they introduced their quarter pounder. It was a huge success. And A&W Root Beer wanted to compete with McDonald's, so they said, "Oh, we'll make a 1/3 pound hamburger, and we'll sell it for less, and we'll wipe the heck out of McDonald's." And so they assembled focus groups, and they gave them samples of their hamburgers, and they said, people said, "Oh yeah, this is really great. It's much better than a quarter pounder." And so they introduced them, and they had this huge advertising campaign, and it just fell flat. And they weren't selling them at all. And so they assembled some more focus groups to see what was wrong. And people were telling them, why should I pay $2.79 for a third of a pound when I can get a quarter of a pound for $2.98? So this is the way. I mean, we're not teaching fractions properly, and so there has to be a lot of emphasis on units, and then how the fraction affects the size of the quantity. There's another story of the same kind. It's much more technical, but I'll tell you. I like it. So everybody knows what NAEP is? Yeah. So, well, it's a while ago now, but in the 70s, there was a question on NAEP. It said, what is the best estimate for 8/9 plus 11/12? And the choices, there was a multiple choice, right? The choices were 1 and 2 and 19 and 21. So you'll see that 19 is the sum of the numerators and 21 is the sum of the denominators. And the answers, student answers, were essentially evenly split between them. So anyway, so we have to understand fractions. And then you have to really make students conscious about fractions and then how do fractions interact with equations. Okay, so the rules are that, so when you have a sum, every term in the sum has to refer to the same unit. I knew a fellow, he's passed away now, but he was the best teacher of teachers that I knew. His name was Herb Gross, and he liked to give people, and the example of, he liked to tell people that 4 plus 3 equals 2. And people would look at him and say, you crazy? What's going on there with this? And he said, no. 4 nickels plus 3 dimes is 2 quarters. Right? So if the numbers don't refer to the same unit, you can get crazy things. And so so the rule for addition is all the numbers have to refer to the same unit, and this is a very good habit to emphasize with your students. And but with multiplication, it's more complicated. With multiplication, the product, the unit of the product is the product of the units. So that's why we have inches times inches is square inches, or a number of objects that you buy with some kind of like pounds of sugar times the price per pound of sugar gives you the price of the total amount. So you have to pay, that gets a little bit tricky, and you have to really, when you have an expression that involves both multiplication and addition, you have to do some work to make sure that all the units are okay. Okay, so this is about fractions, and you have to think about units. And then I think that in transitioning to algebra, there's a new way. You have to think about numbers differently again. And what you have to do here is that you have to forget about individual numbers and just think of numbers as part of a system that has operations that have some rules associated with them. And so that I should say here that there's what algebra is not so clear. In some ways, algebra starts right in the first grade or even in kindergarten. But when it really ramps up and you're studying algebra formally, then you have to think of the numbers as sort of losing their identity and being just things in the system. And then what the system has rules, right? There's like the commutative rule of addition and the associative rule of addition. And those get used in important ways that need to be carefully understood. So we write, right? We write usually a sum of two numbers is 3 plus 4. But if we want to add three numbers, we don't add them all at once. We add two of them, and then we add the third one to it. And if we're being honest, we will show that somehow. The standard way is to put parentheses. So you have 3 plus 4 plus 5, or you could have 3 plus 4 plus 5. But the associative rule tells us it doesn't make any difference which way you do it. And that then has many further consequences. In fact, you can show that from the basic associative rule, that if you write out any number of summands and you put the parentheses any way you want, it doesn't make any difference. It's always the same sum. So the structure of the system and the implications of the rules become the dominant thing. And then as part of this, you have to make sure that students understand the grammar of expressions, which is, I mean, it's not as elaborate as English grammar, but there's some very important rules that are followed, and they're mostly followed to make things easy to write. I mean, like we don't write parentheses in sums because we don't have to. But then you have to worry about minus signs, right? Addition is associative, but subtraction is not either associative or commutative. But when you another thing that happens when you go beyond the whole numbers is that you introduce, right, the reciprocal and the negative. And when you have negatives, if you think of minus 3 as meaning plus negative 3, then you can convert subtraction into addition, and you can permute things any way you want and reassociate anything you want, as long as you migrate the minus signs with the particular numbers. So these are kind of complicated issues which students have to be made carefully aware of, and all this needs to be thought of as part of a system. And then solving, I should say also that algebra problems, what we call algebra problems, have been solved for thousands of years. But what we think of as algebra, namely symbolic algebra, is kind of a recent invention. It was invented in the Renaissance by a guy you probably never heard of. His name was François Viette. He was a minister in the French government in the late 1500s. And he was the first guy to sort of propose writing symbols for numbers. And the nice thing, the point of when you write symbols, right, when you write what are usually called variables, the point is that it doesn't matter what numbers they are. Right, an equation that you will come up with in many algebra problems is a times x plus b equals c, where the x is the unknown and the a and the b and the c are given to you in the problem. And then you solve that by solving. You subtract b from both sides, and then you divide by a, and you get the formula that x equals c minus b over a. And I think, we have the quadratic formula. I think that deserves to be called the linear formula. It was usually not given any credit for being a nice formula. But the point is in that, in making those transitions from the formula that involves x to the mysterious number to the final total, and the equation which solves for x, it doesn't matter what numbers they are. It's the same relationship between the equations. Those two equations are equivalent in the system. And and the numbers can be anything at all as long as the rules of the system hold. So that's a new context, and I feel students need to be made aware of this kind of thing, that symbolic algebra is really about numbers that you don't care what they are. And they're part of the system with the rules. And so the seminar is going to be devoted to studying those two transitions, and we try to figure out, and I'm going to ask for the help of the fellows, because I don't know all the ways to do this, but we're going to try to figure out the best ways to help students make those transitions.